Hi, today I'm going to demonstrate how to derive the four Maxwell equations. There are four equations. One is Gaussian's law, E dot ds divided by epsilon 0. Epsilon is the electrical property of vacuum, known as permittivity. The second equation is B dot ds equal to 0. That is a unique property of the magnetic field. In other words, it is impossible to find a single pole of magnet. The third equation is the Henry-Faraday electromagnetic induction law, where phi b is magnetic field flux. The fourth equation is B dot dl equal to the constant mu 0. Mu is the magnetic property of vacuum, known as permeability. I is current. The second term in this fourth equation is added by Maxwell himself. Where phi E is the electric field flux. So these are the four equations. Can we just label them as 1, 2, 3, and 4? So this is four equation. I'm going to derive these four equations from special cases. In the first place, can we just consider the Coulombs law? If we have a charged particle, a pair of charged particles that would be considered this is Q, this is a small q. According to, and the distance between the two charges is denoted by R. According to Coulombs law, the force between these two charges can be written as K times Q times capital Q divided by R squared. We also know that the electrostatic force can be written as a product of the charge times the electrical field strength, E, where E is a vector. If you just rewrite the K as 1 over 4 pi epsilon 0, then we can argue that these were equal to 4 pi epsilon 0, and that is Q divided by R squared. So by comparing the two equations, we obtained that E in this particular case is simply 1 over 4 pi epsilon 0 times Q divided by R squared. So this is a formula for electrical field strength. Now, if you multiply 2 pi R on both sides, we will obtain that 4 pi R squared times E will simply equal to Q divided by epsilon 0. So what is 4 pi R squared? Well, 4 pi R squared is just the surface area of the sphere. If I draw the sphere here. So you can, if you imagine, if you draw a sphere, then this would be the area of the surface area. So 4 pi R squared would be the area of this sphere. So in other words, we can So this equation can be rewritten as E times the area. So E times the area of this sphere, right? Now, because in this case, the magnitude of the electrical field is constant, so we can multiply that. So we can rewrite it as this form. So that is a left-hand side of equation that equal to E dot product ds. So that is how we can, obtain the equation 1. In this way, we can get equation 1. That is the first equation of Maxwell 4 equations. Secondly, we don't have to talk about the second equation, because the second equation is just the fact that there is no source for, the second equation simply says there is no single source for magnetic field. Let's just move to the third one. The third one is actually built from the original Henry-Faraday induction law. So in other words, the voltage can be generated if you have the change of the magnetic field flux. That is Faraday's law or Henry-Faraday's law. Now, we know that the voltage, have connection with work done. If you time the Q, you will go to work done. If you move a charge along trajectories, if you move the charge along the same path, then work done can be obtained by the product of charge and the potential. So V is a potential. It is a potential, electrical potential. So the work done can be simply written as F dot ds, dl. So that is work done here. Now we know that F also, so because F, it can be simply written as Q times E dot product L. So you can see that the left-hand side can, so in this way, the electrical potential can be rewritten as V will equal to Q as integral E times dl. Okay. Of course, when you actually when you actually calculate the electric field, so you have put the circle. I put a circle here just indicate the integral is go to a complete loop. In the particular case, it's just a circle. So in this way, so we can obtain that the third. So in this way, we got the third equation will equal to negative B delta T. Okay. Finally, we're trying to obtain the fourth one. The fourth equation is actually originally come from Faraday's observation. So Faraday obtained that Faraday observed that if there's a current that goes through the wire, then there will be a magnetic field around it. There is a magnetic field around it. This just represents the magnetic field. This circle just represents the magnetic force line here. In other words, if you want to draw the magnetic field, then that would be, I just draw a single arrow here. So that if you're looking for the direction of magnetic field at any point, then that would be along the tangent. So this is Faraday's experiment. So when Ampere knew this result, he simply used his mathematical knowledge and to rewrite this for this formula as we just write is basically say Faraday actually obtained that B were obtained were equal to mu 0 times the current divided by 2 pi r. So that's Faraday's experimental result. So this result can be rewritten as B times 2 pi r were equal to mu 0 times I. So Ampere argues that in the general case, we should be written as the integral B dl were equal to mu 0 I. So this is a famous Ampere's law. When Maxwell put all these four equations together, he realized that they must have additional mechanism that can induce magnetic field. So Maxwell argues that if you got to the wire, if this wire is connected with, just continue that, connected with a disk, okay? And this disk also connect with another one. So he argues that if you set up this apparatus, and then so there must be an electrical field degree. There must have electrical field between them. And the direction of electrical fields will determine on whether these two sides are positively or negatively charged. Maxwell argues that one can also generate magnetic field. In similar way of the Faraday's experimental observation. So that is how the additional term was added. So this term, so this one, so the Ampere's law was modified by Maxwell. So that you got two terms here, mu 0 I plus epsilon 0 times the first derivative of the electric field flux. So this is how to derive Maxwell's four equations.